Welcome to lesson 5.4, Solving Systems Graphically. So our previous lesson was a review from grade 10, Intro to Applied and Pre-Cal, solving linear equations, specifically linear systems, and we did that both graphically through substitution and elimination. And so those three strategies still apply. We still see them showing up right here. This lesson in particular is just going to focus on solving it graphically. Our next lesson will look at solving systems algebraically. So we have a linear quadratic system of equations is one that is composed of both a line and a parabola. Okay, so linear quadratic, line, and parabola. Okay, what are the solutions of the system? The coordinates of the intersection points. How many solutions are possible? Well, that kind of varies. But the key idea is that, again, we're dealing with intersection points. So just like before, where our two graphs crossed, this is still the case. So what could possibly happen with a linear and with a line and a parabola? Well, if we have a parabola that looks something along these lines and a line that passes across it, how many solutions are there? Well, cross once here and once here, so that's two possible solutions. We can also have a scenario where our line actually forms a tangent to our vertex or another point on our graph. And this would give us one solution. A tangent is where a line will touch a curve but not actually pass through it. Let's see if I can draw this well. There we go. Now imagine that that's like a straight line, not a little bumpy one, where we get a single point where it just touches our parabola but doesn't actually pass through it. That is where we get one solution. We call this line a tangent. Okay. We also have a possibility where our parabola and our line are actually never going to cross. There are no solutions. What's different about these possibilities than our strictly linear systems? Well, in this particular case, we have no scenario where we have infinite solutions because they are two different shapes, so they cannot possibly overlap at every single point because we're dealing with two different types of functions. So let's have a look, see what that actually means. So when we go to graph, option one is that you create a table of values. That is a perfectly viable solution to how do I graph this equation, or these equations as it is in this case. But I really don't like making tables of values. I find it takes a long time, it takes longer to plot on my graph. So what I instead like to do is I like to use my general forms of equations to kind of guide how I draw it. So recall that when I talk about a linear equation, I talk about mx plus b, where m is slope, which can be represented by rise over run. And b is my y-intercept. So it automatically defines a single point. In our particular case, our slope is 2, and our y-intercept is -4. Slope is rise over run, and we've got a whole number. We can say that it's actually 2/1, rise over run. So when I go to plot this, I'm going to put my y-intercept. So step 1 is y-intercept, and then I'm going to use my slope to determine another point. For my quadratic equations, it was always easier to interpret, in my opinion, using vertex form. And we could say that this is in vertex form. So in general, we've got y equals a x minus p squared plus q, where a tells us our stretch or compression, p tells us our x value of our vertex, and q tells us our y value of our vertex. So when we look at the equation we're given, we have no stretch or compression, okay, we have no x shift horizontally in any direction, so my x is 0, and my y is at -4. So my vertex is at 0 and 4, -4. So now I've got some guiding points. I can also state that it's opening up, because it's a positive x squared, even though that's not written. So given this information, I can actually put both of these equations onto my grid. Just zoom out a little bit. So I'm going to plot my y-axis here. I'm going to put my x-axis a little bit higher up, just because I want to make sure that I have enough room for those negative values that are showing up, since both my x-intercepts are at -4, or my y-intercepts are at -4. And then I'm going to label my scale. So +1, +1, -1, and -1. So that's my guiding scale. I've labeled my axes, so now I can plot my points. So I'm going to call this equation 1 and this equation 2, just for the sake of labeling. For my line, I'm going to find my y-intercept, which is at -4, and I'm going to use that rise up to over 1, and it's going to help me plot some points up to over 1, up to over 1. And then I can connect those points, excuse my cheating. You know what? I don't know why it keeps insisting on using that highlighter. You'll have to bear with me drawing this line in then. You, again, would benefit from using a ruler. I just can't on my surface. So I've got equation number 1 here. Equation 2, I know my vertex is at 0 and -4, so I'm going to plot this one in black. I haven't stretched it or compressed it at all, so usually it's 1 squared is a 1, so I go over 1, up 1. 2 squared is 4, so I know that sounds strange because it actually ends up being 0. 2 squared is 4, but then -4, which is my shift, right, takes me down to 0. So that's how that kind of works, but it can still follow the same shape. as a regular x squared parabola. Here I'm going to draw in my parabola a little bit. Make sure it's nice and curved here. And I can see I've got 2 points where my line is crossing my equation. So my solutions, I'm going to have 2, are going to be both of those points. So option 1 is at 0 and -4. Option 2 is at 2 and 0. Now when we are writing our solutions, remember that they are points. That means they get round brackets around them and commas between the x and y value, always listing your x first. Do not drop those brackets around that. I noticed that happening a lot in our quadratic equations and graphs unit. That was unit 2. So do not drop your brackets on your coordinate points. Quadratic systems of equations are our other option that we're going to be running into here. And so they're both going to be parabolas. So we've got a few different possible solutions, but the key thing is we are still looking for intersecting points. They're both parabolas. We are looking for intersecting points. So option 1 is going to be when they directly overlap each other. How many solutions would that give us? Well, that is infinite solutions. And this is because they actually have the same exact equation. So all points match. Okay. Option 2 is when we have 2 parabolas that are never going to cross. This specifically is going to happen when we have one opening up and one opening down, and they have vertices that do not overlap in the slightest. So my opening down is below the one that's opening up. That is going to give me 0 solutions. Option 3 is when they share a vertex, but again, one's opening up and one's opening down. So again, this can be a vertex. It also could hypothetically be a single point where they're off to the side of each other. So this actually also applies if I'm dealing with a parabola like this and one that goes like this. They still only hit at a single point. Finally, I can have parabolas that cross, in which case I will have 2 solutions. We also only have one solution if we've got them both opening upward like this, as long as we don't have different stretches and compressions. So we've got a few different options for how to get a single solution. So let's check this one out. Again, I really like vertex form because it lets me find my vertex very easily, and then I can extrapolate how did I stretch or compress my quadratic. So looking at equation 1, and again, I'm just going to label them 1 and 2 for myself. So looking at equation 1, I can say that my vertex is at 0 and -16. I could also figure out that my y-intercept then is at -16. My x-intercepts, this is a factorable equation since it technically also is in general form, and that is a difference of squares. So my x-intercepts are going to be at sorry, positive 4 and negative 4, and it's opening up. There's no stretch. So that's going to help me draw graph 1. Graph of equation 2. My vertex is at negative 4 and 0. My x-intercepts going to be at my vertex, so I don't really need to worry about that. But my y-intercept I do need to define. And so I plug in 0 for x. 4 squared is 16, and there's a negative, so negative 16. It opens down, and there's also no stretch. That opening down is that negative out in front, but since there's no actual value, there's no stretch. So because I've got a vertex opening up and opening down, but I need to reach negative 16 on my grid. Again, I'm going to have my x-axis a little bit higher up on my graph. So I label y, and I'm going to put x actually all the way up here so that I can get to negative 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and even then, I'm not going to get to 16 just by counting by 1, so I'm going to have to go down by 2 and up by 2. I'm still going to leave it by 1 in each direction on my x-axis, though. That is totally allowed. You are allowed to have different scales going left and right. The key is just to remember that you have, in fact, done that. So here we go, graphing equation number 1. I'm going to put my 2, 4, 6, 8, 10, 12, 14, 16. My vertex is at 0 and negative 16. It's not stretched or compressed, so I'm going to go over 1, up 1, over 1, or over 2, up 4, over 3, up 9, 6, 8, 9, and then over 4, and 4 is where I have my intercept, so that's going to be there. So that is equation 1. Now that over and up thing that I was talking about, that's just following the same pattern as a regular x squared parabola. So 1 squared is 1, 2 squared is 4, 3 squared is 9. So that's how I was figuring that out. For my second equation, and I'm going to label that number 1. For my second equation, my vertex is at negative 4 and 0. Draw it in there. Okay, my y-intercept is at negative 16. It's opening down and it's not stretched or compressed. So again, over 1, down 1, over 2, down 4, over 3, down 6, 8, 9. I have these points defined here. So by filling in my curve like this, I'm able to easily define where my 2 points are crossing, which is great. I'm not done though until I actually write my solution. Oh, scrolled too far. So my solutions are going to be at negative 4 and 0. That's 1 point. My other solution is at 0 and negative 16. So the key thing to note is that our solutions are where our graphs cross. We need to be very precise in our graphing. So you'll notice that I'm not sketching these graphs. I'm using grid paper and I'm actually plotting very specific points. So when you do your homework moving forward, please make sure you are using graph paper. There is some available to you in the classroom, so there's no excuse why you're not using graph paper to do your homework. In addition to that, most of the questions in your workbook actually do have grids with them if you are creating graphs. So good luck. Ask any questions if you need, and then we'll move on to algebraically.